can also recap a few things that we did last time, again here. And mainly just, first of all, let's just recall that we have two different problems, right? We have the problem of prediction. In the problem of prediction, we're somehow dealing with an offline setting, right? So we have your policy fixed. You just sample with that policy, use those samples to just train your model. So this is less stress, less online as compared to the control problem. So in the control problem, while you're sampling from your environment, you want to somehow build a kind of clue about the optimal policy, right? And this means that your policy improvement should be somehow merged into the loop of value estimation. This is exactly the same thing we did with SARS and Q-learning in the previous chapter, and we want to repeat it here using function approximation. So let's get into the control part. And in the control part, if you remember, we had this loop which was somehow extracted out of the generalized policy iteration, right? So in GPI, we basically start with a policy. We just evaluate that policy. Then we know how to improve that policy. Then once we improve that policy, then we go back and again evaluate the new improved policy. We find the Q values, we update again, and we keep on going, right? So that was GPI, but we saw that if we want to just build GPI kind of loop, then we're going to get into this trouble that we stick to one strategy all the time, right? Because we're always doing greedy. This is not a good idea. Then we basically added this epsilon greedy here. So instead of just being greedy every time, once you improve, then either you play your improved one or you just randomly go somewhere, and this is going to help you explore the environment more. And one other key factor about the control loop was that now here we are not going to really evaluate the policy anymore, right? So you just update, correct? So you just sample. Out of that sample, you're going to update your Q function. And with this new Q function, you are again going to play epsilon greedy, right? And basically, your Q function is getting updated with a single sample of that policy, but you don't care, right? Because we talked about this, that this iterative loop is robust enough that once we just go over all the states enough number of times, then everything is going to work fine. So we basically want to do the same thing here. The only thing that we want to change is that instead of estimating or policy or a Q function based on a table, we want to do it by a model, right? A deep model. Now, which line here in this loop is going to be the line where we integrate the neural network in? Yes, go ahead. Line 3, exactly. So this is going to be the line where we are going to put the function approximation, right? So instead of updating the table, we are going to update the weights of the model, right? And we do it again the same way that we did in the tabular case, but this time we just, instead of working with the table of values, we are working with parameters. So now let me just define Q network. You already know what Q network is because last time we basically defined that Q network, but if we want to now, a Q network is basically that network which is going to look into the feature representation of one state, and at the output going to give you the Q values, those action values, of all possible actions at that stage, right? So you're in this particular state. You're going to give the feature of that state into your neural network, right? It depends how you represent that, but you're going to give it to your neural network. That neural network tells you, okay, if you do this action, you're going to get this value. If you go this action, you're going to get this value, and so on, right? So this was basically what we defined. So we said that, well, if you think about a single pair of action and value, then you're going to have one representation for every single pair, and then they're going to be m, where m is the number of actions. You have m different of them stacked together, but you can look at the whole thing as one giant neural network, which is taking the representation of this state you are in, where you are right now, and then it's going to tell you is roughly the Q value for every single action that you want to do, right? So that is the Q network. Well, this is not something new. And usually people, I mean, when you put here deep neural networks, then people call it deep Q network, DQN, right? So if you hear DQN, that is basically this guy, right? Now, deep Q network is a kind of value network that you usually use if you want to do any value-based kind of control. Whatever you know up to this point is value-based, right? You always work with values. Can we work without values? Well, you can. I mean, practically in case, then it's going to be policy gradient method, right? And then at the end of the day, there you again need a sort of value estimator, which ends you up with the action critic approach. No worries, we're going to get into them. But what we have done up to this point is that always we work with values, right? Whenever we want to control, we always estimate the values. And based on those values, we decide, right? We never work directly with a policy, right? We don't play with a policy and say, oh, let me make it better, right? We don't know how to do it, right? We're going to talk about it later. Because always we need the value to somehow understand how this policy works. So any value-based approach that you do, it means whatever we have done up to this point, you always need, in the like a deep form of it, you always need to have a Q network for that. And that is obvious because you're in one state, you want to know what is the value of every single action that you can do, right? So that is DQN. And a DQN, basically, it could be a simple MLP. So here you have the feature representation. This goes over the neural network. At the output, you have exactly the same number of output as the number of actions that you can do, right? So if you're walking in a 4 different outputs, right? Given the state that you are, the cell that you are, it's going to explain you what is the value of going up, down, left, right, right? For more complicated environment, again, this is going to be the number of outputs you have. One thing that you should pay attention here is that we are, as I told you, still talking about discrete number of outputs, right? Discrete number of actions. We haven't got into the case where you have continuous action space. That is the thing we're going to do next, okay? So now, I told you any value network, including network, is basically a neural network, and then it can take the representation of the state, right? For instance, if you are considering this kind of game, right? Then what is the representation of state that you are in? So this state is more complicated than a grid world. You cannot simply represent it with one hot vector or the location that you are in, right? There are lots of factors being involved here, right? And then if you're, for example, considering a computer game, right? And then the easiest way for you, or the most practical way, is that you say, okay, one frame or maybe multiple frames of the game is the state that I am in, right? So I'm right now playing chess. I take a photo of this chessboard. This is the state that I am in, right? And you don't need to really extract anything out of it. You can directly give it into a convolutional neural network, right? It's going to process that image for you, and it's going to give you at the very, very output a bunch of numbers. The number of outputs you need is exactly the number of actions you have, right? So in this game, you have, right? Left, right, right? So what is the number of outputs you get here? 2, right? So you give this one. Maybe you don't give just this guy, which is an RGB image. Maybe we don't give only the first 3 channels. Maybe you just consider a frame of like 10 frames stacked to each other, right? And then you get all of them. So each of them has 3 channels. So it's going to be 30 channels going inside this neural network. At the output, you have 2 values, right? And they are the value of every. So here you have to put a tensor which is collecting the frame that you are playing right now in, and then at the output you're going to have the action values, which is basically giving you the value of every single action you can do, right? So we talked about this, that when I represent here A to be like with a bold face, a vector, I simply mean all the values, right? So it means that here A is right and left, so this guy is a vector of size 2. Sorry. Q of that particular state acting left, Q of that particular state acting right? So now, if you have a Q network, then the question is to control, and we talked about this. We have two different approaches for doing control. One of them is on policy, right? What is on policy? It simply means that while you're playing, you're improving the same policy that you're playing with to get better and better, and gradually it converges to the optimal policy, right? So SARSA was the big example, and then if you use deep Q network to an approximation, then this is what you are doing as deep on policy reinforcement learning, right? So you are on the policy, you're just updating your neural network instead of the table of the Q values, and based on that, you're just designing you're improving your policy. You keep on playing with the same policy always, right? And as you play with that policy, you just train your neural network to estimate the values of that policy you are playing with, right? Now you hope that your policy gradually gets to, then that Q network is going to gradually up values, right? So this is on-policy reinforcement learning, but you can also do off-policy reinforcement learning. Basically, you can do Q learning using Q network instead of the on-policy one, right? So in this case, you're basically doing importance sampling. Again, here in this particular example of deep Q learning, you basically don't do that kind of importance sampling that we really think in general about, but more appreciated when you are working with deep reinforcement learning. Now, what is the reason for that? There are a bunch of reasons, but the most important ones are these items that I have said here. Basically, if you work off policy, you are more sample efficient. What is the reason? You don't need to write now anything about how we do it. Just recall what is the difference between off policy and on policy. When you are on policy, you're sampling with your policy and you are estimating the value of that policy, right? This means that only the fresh samples are valuable for you, right? A sample which you got long time ago is useless because it was done by a very bad initial policy, right? So you have to throw that away, right? But if you are playing off policy, you do know that you are not evaluating the policy that you are playing with, right? You are evaluating one other policy, but you somehow manage to use samples of other policies as well. This means that the policies, the samples you collected at the very beginning with your worst policy is still valuable, right? Because that this off-policy doing deep reinforcement learning is much more efficient because you can use the samples that you collected before again and again and again, right? And this is basically the same thing that we do in deep learning, right? In deep learning, we are always limited in data, right? And then we want to collect some data and use it over, right? And off-policy reinforcement learning is going to let us do that, right? Because of that, usually we are more interested in deep off-policy approaches. This is why you hear about deep Q learning, but you don't hear too much about deep version of SARSA, okay? So we're going to talk about that you don't get, you're not supposed to understand these terms right now, like experience replay and sample efficiency. But you're going to understand it as you're over with this part, and you get the idea why deep Q learning is better. Okay, yeah. Oh, definitely, yes. Yeah. Oh, overfitting. Let me think. Yes, that could. Yeah, but then this means that it depends on what you're doing, but in this simple value network or Q network, this simply means that you're somehow getting stuck to one suboptimal solution because you just get stuck to a sub part of your status space or action space. Policy is more vulnerable to that, but it's, I mean, at the end of the day, when the space of the like state space is very giant, eventually you're always dealing with overfitting, right? Oh, I don't know. What do you mean by less variance? Oh, you mean in terms of the policy? Uh, oh, yeah, because of, like, if you do off-sampling. Like here, if you think only about deep Q learning, I mean, the variance does not show up that significantly. The reason is that, well, in deep Q learning, we are somehow bypassing all of the important sampling process. We're a bit cheating there, right? And because of that, we don't see that variance issue. But if you think about a general sampling and then you do off policy or on policy, it means that in the off policy you really use important sampling, then that's correct. But that is something that you see more obviously when you do policy gradient methods. Because there, again, you're doing one policy, and you get one policy, you play with that, and you collect one sample. But then you want to improve the same policy network. So you're going to use the samples with the previous policy to just update into a new policy. And there, you have nothing but to do exactly important sampling. And when we do that, then potential important sampling can increase the variance. And this is one of the reasons that your model could quickly get out or diverge or get into a kind of very bad sort of local minima. And how we can get rid of that, we need to just restrict or trust region. And this is basically TRPO and then PPO algorithm. So we're going to talk about that later. You could say somehow here, but it's like less stressed, right? So usually what you see is simply because of this state space. No question? Okay, so now let's start with the on-policy case. On policy, simply to just warm up a bit, to just see how we can do this on policy there, because on policy usually sounds more intuitive to just develop. And then after that, we're going to get into deep Q learning. So now, one thing you might tell me is that, I mean, I'm not 100% sure that this is any more the case right now, but old days, with less amount of information out there regarding this deep reinforcement learning, people would ask this question, like, you talk about value networks, and what are the value networks in general? Is it simply Q network? Well, Q network is one value network, right? So you could have Q network, which is computing the Q function. You could have the value network that I told you before, right, when you want to do the prediction. And then in that case, that one is again a value network, right? Any network looking into your state representation and computing any sort of value that is a value network, including the Q network. But Q network is the serious one. It's the only one which we use in practice, really. So yeah, just to avoid any confusion. So when I say value network, 99.9% of the time, I'm just talking about Q network. Okay? So that being said, then you might say, okay, is there any other kind of network? I already told you there's something called policy network. It means that you have a neural network which is looking at your state in action and tells you what is the policy, right? Or what is the probability. And then we're going to talk about that one as well. This is the topic of the next two chapters. So, but right now we're just working with the value networks. This means that we are just doing value-based reinforcement learning yet. And in that sense, then this is one, the very first version of the algorithm that we are developing. So this algorithm that you see here, this is basically what we did last time when we wanted to use or model So we wanted to train our value network, this value network V, to predict what is the value of one particular state. So we started to sample from the environment, get the TD estimation out, TD samples out of it, use those TD samples to train our model. That was the idea, right? And then we started to write it down. So we could basically just do it for a Q network as well, right? So if you want to train a Q network, we just did the same thing, replacing all these with Q except this guy, right? So let's just look at it again to recap, and then just make it online or control one. So what we are doing, we are sampling one trajectory. This is the trajectory we sample from. Now, once we are in one particular state, say we're at S0, now we want to get one estimate of the value for this S0, right? And how we do it, if we think about TD0, for example, then we would say whatever the immediate reward is, R1, plus the value of the next stage, right? And the value of the next state, it simply means that I look at the next state, which is S1, right? I give S1 to my Q network. At the output of the Q network, I'm going to have a bunch of Q values. I average them with respect to policy. It's going to be the V value, right? So, and I use that V value added to this reward as the estimate of the value of the state S0, right? Clear? So this is the estimate, the first term, minus, that minus comes from that gradient, right? When we wanted to compute the gradient of the MSE, or that least square term, then we had this delta times the gradient of the network, right? And this delta is the same thing as we had before. So this is the sample that we have minus, this is the output of the network. The network for particular state S0 is giving me this kind of Q values. I am looking into one particular action, so that is AT. So I am looking at the particular output of my neural network at that stage, right? And then this is the estimate that I have. I want to update it, so I compute this delta using the new sample I got, right? So you compute this delta, you multiply it with the gradient, right? If you want to do eligibility tracing, we talked about it. That one simply means that you are doing a moving average over your trajectory, right? And that was 7, right? So basically, that eligibility tracing was nothing but you get the gradient each time, you multiply it with a number smaller than 1, and you add it up to whatever you had before, right? And you keep on going like this, right? So that was the eligibility tracing. Now what you are doing, you are going to update using gradient descent again, right? This is your new weight for your model. So how you update it, you're going to multiply alpha, which is the learning rate, to your gradient, right? And this gradient is delta. That is the first term inside the gradient. The second guy is the gradient, the back propagation on your network, right? So we are replacing that gradient, the sample gradient that we had, with line 7, which is or Q values of one particular for one particular environment, right, and one particular policy, right? Everybody recaps, right? Okay. Now, how we can make it now online? Well, if you remember in SARSA, we somehow got rid of this V, right? We replaced it with Q. What was the trick? What was the trick? So we said, like, okay, we are in this particular word. We want to know what is the next state in action, right? The next state is given by the environment. For the next action, well, we update our policy first. We draw that action. We don't apply it. We just draw it, right? And once we draw it, we say, okay, we know the next action, right? And then instead of using the value of like the average one, we are going to just replace the Q value of the next state and next action, right? So we can do the same thing here. So we would say next state ST plus 1 is the average of the Q output over all possible actions. But since we have access what we can do, we can just do work on policy, right? We just have access to that. So we can just policy action, just to reveal what is the next action. So we're going to do that. We would say, okay, what is the next action for the what is the action when we're in the next state? Well, we have the Q network. We do know how we are going to act. So we are going to act, right? And this is the next action. So we are going to replace this guy simply by the Q value of the next action, right? That was ours. State action, you get the reward. State, you do act, right? You know what is action. Then you replace that, right? Everybody's clear, right? Okay, so that is the only trick that you need here to just make it on policy online control, right? And then you can simply have this on policy online control. Okay? So what we're going to do, we are going to start with the trajectory, and each time we do have the action of that time because we sampled it in the previous time, right? So we get that state in action, we just act, we get the reward, and we have the next stage, right? Now that we have the next state, you can give that next state to your Q network, right? And out of that Q network, you do know how to play epsilon, right? Because you have the Q, right? I give ST plus 1 to my neural network. That neural network is going to tell me what are the actions, right? And then or the values of those actions, sorry. And then I can just use epsilon greedy based on those values to act, right? I do act, so I'm going to sample 180 plus 1 from that policy, right? But I do not apply it to the environment. It for updates, right? Now I have this complete one-step trajectory. State action, I get the reward, state action. And then when I want to update, I basically replace in line H. You see this? Only instead of V, I'm going to replace it with the Q of the next state and action P, right? So that is going to be my sample, RT plus 1 plus gamma Q, ST plus 1, AT plus 1. This is basically, I would say, what is the immediate reward I get. And since I am on policy, I do know that in the next state, I am going to act AT plus 1. What is the value of that guy? I'm going to add it up to my immediate reward. This is my estimate or my sample estimator of the value, right, for the current state, right? I have this sample estimator, the state action value network, right? And then I update, right? Everybody's cool? Yes. No.
Usually with deep learning, there's a label. There's a true value.
Right.
Where is that here?
The label for you is RT plus 1 plus gamma Q ST plus 1 AT plus 1.
So that is
the label.
Truth, I guess.
Somehow you consider it the truth. Yes. It's not the truth. It's just an estimator of the truth, but you don't have anything else. So you take it as the truth.
Training the network, you're not actually like taking the screen, telling it what you think the Q is, and training it that way.
Yes, this is roughly the same thing, right? But the point is that you give it to the same neural network, right? So you give it to the same neural network, but you say that you just do one action, right? You get next stage, right? Next frame. You give it to your neural network, and then this neural network is going to say that if you do action 1 or left or right, these are the values, right? And then what you know, you would say, okay, I want to play epsilon greedy, that this means that I would most probably go to act right? Sample, right? Randomly see what's going to come out. So you sample, it says go right, right? You don't apply right yet, right? But you know that once you want to play, you're going to press right. So you're going to use that fact. You would say, okay, since I'm going to go right, then the Q value is 1 approximated by the network, right? Now, I got my immediate reward, right? So immediate reward plus that guy is now an estimator of what you want to see, right? As the value of your previous state, right? Right? So you take one. So this is basically your label, right, this red one. And then this is the guy who you want to train, right? So you would say that my Q value at the current state, given that I did this action, I want this value to be close to this guy. Because following information, I am assuming that this neural network is eventually converging to something solid. This should be the value I would see. Right? Yeah. And this is very interesting that you see it in form of label, because we're going to have problem with label. And yeah, this is a very good, I'm happy that you see it like this. So as your friend said, this red guy, I'm going to clarify it more later, but you can think of this red one to be a sort of label, right? So you do one particular action, you are building some sort of label for your Q network so that using that label you can train your Q network, right? So you would say, okay, this is state and action, go there. Then at the output, I didn't have one label to just do supervised learning, right? And what is that label? This is the estimate you get out of TD, right? But we're going to talk about it more later. Okay, cool with this loop? Right, yes? Yeah, we talked about this. So the original one gradient is this guy, like Q minus this one. And we just flipped them so it became minus, right? So you can think that maximizing. So this is the delta, and then the Q propagation over the network itself, right? Now, one thing that you can do, you can obviously here I am just updating with my sample gradient, right? I can make it the momentum over the trajectory, which is going to be eligibility tracing, right? So you can do it with eligibility tracing. This means that, say that every particular state and action that you are, once you computed this gradient, you're going to somehow compute the moving average with whatever you have. Is where you have seen one particular state in this trajectory, right? And then out of that, you can actually end up with the Sarsa control loop in the deep version, right? Instead of using a table, now you're using a network, a Q network, right? So eligibility tracing, as I told you, it's basically nothing but computing a sort of moving average on your trajectory. The whole interesting point here is that the eligibility tracing in the tabular case was a sort of moving backward and see where you had been, right? So at every single stage, you were updating this trace of eligibilities because you wanted to say that, okay, I have seen this particular state a couple of times, and each of them had been there and there and there, right? Now, this is somehow connecting to backpropagation, right? But it's like backpropagating over your trajectory. Like you are going back, and the more back you go, like there, if you think, but basically everything comes out of the math. Yeah, it's a kind of interesting connection. Like in backpropagation, you're just sending backward the gradients, but now you're not only sending it backward over the network. Once you sent it backward over the network and you got that gradient, you get this gradient and you send it backward. Been before, if you had seen this state, get this gradient and update, right? And then that gradient is going to somehow get a scale with the corresponding weights of those particular states, right? And this is going to impact the update of your in the neural network. If you think in that sense, you can think of like stacked neural networks in front of each other on the trajectory, and somehow everything backward on the whole giant neural network. Yeah. But yeah, that's, as I said, it's just intuition, right? Everything comes out of the math. So doing that, the only thing that you need to change is basically this line 9, right? So whenever you computed one sample gradient, then you are going to just update it with that moving average is trajectory that you're moving, right? And then one thing, again, it's interesting that your friend also mentioned, you should think of this red guy to be the label, right? It's like every single time you're building some sort of label for yourself to train that neural network. And how you're building it, basically use TD, right? TD plus your own network. Why? Because you don't have anything else, right? Cool. So that is the idea of SARSA. As I said, you can do it. It doesn't mean that no one is using that. But this is less popular as compared to deep Q-learning or deep off-policy approach. And the deep off-policy approach is basically using this benefit that since you're doing some sort of importance sampling, you're not obsessed with having examples of your own policy. So in off-policy, you're able to basically evaluate one target policy pi bar based on the samples coming from another policy pi. This lets you that you play with one policy, right? But then you evaluate another policy, right? This is why we call it off-policy, right? And then this means that whatever sample you get with any policy, you can always use it in this approach, right? Because those policies, again, are connected to the target policy by some ratio, right? Importance ratio. And this means that samples you collect are not getting totally outdated, right? So you can go over them over and over. This is the whole idea of doing off-policy in the deep learning, deep reinforcement learning. Now, the most important one is the deep Q learning, which we are going to do. And that one, you're going to see that again. You can use your previous samples. You can do the experience replay. You go over them over and over to just train your network, okay? So what was Q learning? Q learning was an off-policy approach. So same thing as the main framework. We had two specific policies, right? The target policy was, what was the target policy? The greedy one, right? The best one, like you don't do any epsilon, right? But with what was the policy that you play with? It was the epsilon greedy, right? So you play with epsilon greedy, but each time you try to evaluate the greedy policy, right? And since you are evaluating the greedy policy, you already know what is your optimal policy, right? Because greedy policy or evaluation of the greedy policy is giving you the best Q values, right? And out of that, you can always find out what is the optimal policy. So that was the kind of update we do. So we were pretty much doing the same thing as we did in SARSA. But in SARSA, once we want to know what is this value to build this label with, right? So this was the immediate reward. Then we need to have the Q at the next state, one particular action, right? So in SARSA, what we do, we act, right? We just sample from our policy. We know that we are going to play 80 plus 1, so we're going to put 80 plus 1 here, right? Now, when you are doing Q learning, you would say, I don't care. My target is greedy. And what do I do in greedy? I'm going to look at the output of my Q network, and I'm going to do the action which has the maximum value, right? So this means that you only need to know what is the maximum value of that output, right? So this is going to you in the next action, right? It only depends on the Q values, right? And because of that, you're not doing on policy, you're being off policy, right? Your next action, well, it might be the maximum one. Right? So that was the idea of Q learning. And the only thing that we need to do again is to replace these guys with the Q network, right? So basically, this guy is going to play the role of the label for us. This guy is the network itself. and you update with that, right? Everybody's cool? Okay, so this would be the case with a neural network, so with a Q network. So what you're going to do, you go line 6, you go and you act action AT coming from this particular policy. Then once you're in one particular stage, you're going to get the immediate reward and you go to the next stage, right? You don't need to find out what is your next action yet, right? You just give the next stage. It's going to tell you, well, these are the get at this stage, right? And you would say, okay, if I want to play greedy, it means that I'm going to do what you see in line 7, right? So I'm going to get the maximum of the output of my Q network, right? I'm going to look at my Q network. If I wanted to play greedy, I would do the action which is maximizing everything. And then the value that I'm going to collect is going to be that maximum value, right? So I'm going to get this guy. I add it up to my immediate reward. This is the sample reward for the greedy policy, right? So that is the sample for the greedy policy. My network itself is actually estimating the value of the greedy policy, right? So I would say, what is the value right now for my current state in action? Well, this is the difference that I see, so I'm going to update with that one, right? So you compute the difference. That difference goes along with the gradient of the network, right? And then you can update the parameters of your network. Everybody's cool? So you don't need to know your next action, right? You start from one state, you act, you see the reward, you look at the next state, ask your neural network what would be the greedy value. Yeah? You build your label, then you try to tune your neural network in a way that the values coming out of it are somehow matching this sample, right? Then in the next time, again you act, right? Your action is not anymore greedy. It's just epsilon greedy, right? You could be totally random, right? You do one other action, and once you do the action, you're going to get the Q values for that. The immediate reward in the next state. In the next state, you have an estimate of all the action values, right? Again, you take the maximum one. You would say that is what greedy would do. You build your label. You try to tune again your neural network that is matching this new sample, right? You keep on going time, right? Every time you look at your next state, using like this off-policy mechanism, you would say, what is the sample value I would get, right? And then you try to play with the weights of your network such that you see that value, right? You keep on going in time. Gradually, this is going to get what you want. So, yeah. Question? No question? So this guy that you see, this is the basic deep Q learning algorithm, but this is not going to work. So if you implement this, it's not going to work, right? And there are a bunch of reasons for that. One of them is that we're not doing experience replay. We're not reusing the samples that we had. So we are actually getting super sample inefficient, right? And the other reason is that we're actually using the samples which are coming next after each other. They are highly correlated. They are not good for training. The third reason is that, what is the third reason? Okay, I also forgot, so I need to check the slides. The third reason is that we are using the same network for labeling and for training, okay, for evaluation. And then to get rid of that one as well, we need to define the concept of target network. So we basically copy one network to evaluate, and we just update it once upon a time, right? So if you do these stuff, then it's going to be that breakthrough which came up with the Nature paper, and everybody say, oh, neural networks can be used for reinforcement learning, okay? So maybe